Okay, here we are. Here we are again. So as I said, I am a chemist, not a biochemist, and I work with rarefied um, reactions. Okay, so that's a picture of my lab. Nothing to do with the test tubes and anything typical of chemistry. Sorry. Almost by chance, I was involved in this very interesting topic that we are all interested in, which is astrochemistry and of course also cosmochemistry. And that brings me also to get interested into so-called prebiotic chemistry and astrobiology, which is the main argument today. So this is just a list of various projects. Some of them are already concluded, some are still ongoing, and then we have just two new projects that started 1 week ago. So it's a NASI project on prebiotic chemistry again, and then actually also some chemistry in space, this time in a little bit different way, because in this other project that we have just have financed, we are going to study the reactions of several species which are still abundant in the terrestrial thermosphere and polymers of space technology interest. So that's I've been in the business for a while, so I'm. Many of you know me already, but I have a lot of interaction with astronomers, so I know you guys. So I know that you call carbon a metal, which is terrible for us, and many other things. Okay, joking apart. Uh, I'm still a chemist in spite of all these collaborations with astronomers, and I still see matter and the universe is made of matter, baryonic matter. That this is the one I'm interested in because we don't know what is dark matter yet. The only one. But I would like actually to study chemistry of dark matter. So it's an excellent project, in my opinion. It's a bullshit thing or not. Fantastic. Okay, joking apart, when I look at a galaxy or the universe, what do you see as a chemist? Well, I see very simple molecules. Those are the molecules which are most abundant in space. But of course, we ended up somehow to life. And so there must have been some chemical differentiation. That's a term that we normally use. So for sure, we had increase in complexity going from the molecules which are more abundant in our galaxy and also in the other galaxies to the molecules that you see there. As an example, you see a segment of DNA that you might recognize, and then there is a protein. So it's a very special protein. This is gluten, so maybe you have problem with it, or maybe not. So just to show you how complex are, and it's not a complex actually protein. It's a simple protein in gluten. So there are proteins which are much larger than that. So clearly there has been something going on, So we are a little bit. Life is a little bit bizarre in the context of the universe, but of course we are part of the universe. Okay, so somehow we uh, we have been generated starting from very simple molecules. Okay, so now I will use my title. It's like a joke. You should never explain a joke. So if I'm explaining a title, maybe that's a not good sign, but it will be the outline of my talk actually. So we will start by speaking about prebiotic chemistry. So what is it? Little prebiotic chemistry. Why do we care about it? And then we will see how this can occur in space. Is it easy or not easy? Well, prebiotic chemist is the chemist that finally is supposed to have led somehow to life. And so where did it occur on Earth, elsewhere, and where? Before or after solar system formation. So in this chat, I'm going to tell you what I know about the subject, and especially from the perspective of a chemist. So maybe this is a little bit new to you in the sense that maybe of the topics I'm going to touch, you are familiar with them, maybe more than, for sure, more than me. But in all cases, I will suggest you what I do see when you speak about these kind of problems. Okay, let's start by defining what we mean with prebiotic chemistry. Well, the idea is that the original life on Earth is believed to have required the reaction of organic compounds. So we are not talking about simple chemistry. We are going to speak about organic chemistry. And somehow these organic compounds find a way to organize themselves and form the first protocell, the first replicating entity, whatever you might think of. And prebiotic chemistry is exactly the systematic study of all the chemistry that preceded this part. So as a matter of fact, we speak about organic chemistry in a way. Organic chemistry in extraterrestrial environments, so not the organic chemistry that my colleagues in my department are doing in their lab, of course. So that's the topic we are dealing with. The question is that, what do we know exactly about this process? Well, not much. Unfortunately, not much, because the processes that led to the rise of life, to the birth of life, are no longer active. So that's the main point. They are no longer active because as soon as life arose, it immediately used all the available resources. That means the other organic compounds. So at the moment, we have no idea because these processes are not active anymore on our planet. So we don't see them happen. So we try to think how they happened in the past, but we have to use, we have to follow some clues because, as I said, these processes are not active anymore. There is another problem, which is also almost as serious as not to have them ongoing. And the other problem is that the geological record that helped so much to understand the biological evolution stops too early. So the most ancient rock has roughly 4 billion years. And there are some, there are clear evidence of the life ongoing 3.8 million years ago. So that means that we don't have, the information coming from rocks, which are very important, for instance, even to know the composition of the terrestrial atmosphere, that's very relevant. And of course, we don't have a fossils. So in a way, we have to work blind. We are blind in some way. And so it's very interesting to look around us then, since watching to our own planet, we don't learn much. So it's very interesting to see around us. So as a chemist, I will start by considering elemental composition. So we always behave this way. First, elemental composition, and then we see the kind of molecules that you prepare with those elements. But elemental composition is the first step when you analyze, from a chemical point of view, any system. Okay, so let's analyze life from this point of view and compare life with our own planet and our galaxy. And there is immediately something that, that I notice immediately when I check this kind of tables and elemental composition. Okay, if you look, we are more similar. I mean, the chemical composition of life is more similar to the chemical composition of the galaxy rather than to the chemical composition of planets. So I provocatively wrote, are we aliens? So are we coming from outside the Earth? Because indeed, we are much more similar to the rest of the universe as far as the elemental composition is concerned, because then the kind of molecules are very different. I show you, the simple molecules abundant in the universe and gluten and a segment of DNA. But really, we look a little bit bizarre, no, in our context, because hydrogen, oxygen, carbon, and nitrogen, these are the most abundant elements. I'm talking about molar fraction. Chemists don't think about masses, but molar fraction. That's another difference with respect to you guys. And the same sequence, apart from helium, helium doesn't do much anyway. So the same sequence is present in the galaxy. And the situation is quite different in the case of our own planet. And then, of course, not only the elemental composition, as I said, it is also important the chemical aggregation of the elements that we mentioned. Okay, so what do we think? This is better to say, what do we think with respect to what we know about the basic steps that finally brought to the origin of life? Well, everything started, of course, with the formation of the solar system and our planet. So it has been estimated that it took 300 million years to have a stable hydrosphere, because, of course, melted rock is not good to have liquid water around. And then, according to the common sense, I mean, there is some consensus on these milestones. The idea is that there was somehow organic synthesis. But pay attention to this aspect because this is kind of important. This organic synthesis that supposedly occurred on Earth before life must have been massive. So I insist very much on this concept. Must have been massive. Why that? Because we don't know how you pass from a complex molecule as complex as you wish to the first living entity. We don't know. And we know the outcome. So we try to reproduce this chemistry in the lab. We have tried a lot to reproduce this chemistry, knowing also the ending point. So that's a great help because we know what we do expect to have. And so yet we have not been able to reproduce these processes. So that means these processes are highly improbable, not obvious at all, because if they were obvious, we would have been able to find them. Okay, so that means that by chance, totally by chance, putting together these organic compounds, we don't know which organic compounds, how many, but for sure the probability was small that life spontaneously evolved from these organic compounds. So that means that you expect that you have plenty of them. Plenty of them means a lot of, many events, and all this little probability that that specific event would occur, finally find a way. So there must have been a situation where we had somehow this huge amount of organic compounds around. And then from this, okay, that's the common sequence. It is believed that there was an RNA word before a DNA word, because RNA is simpler, because RNA can do both metabolism and the genetic code, and DNA is a little bit more complex. So it is believed that that happened later. And finally, we had the last unified common ancestor from which all the living entities now originated. But this is not part of my work because, as I said, I'm not a biochemist. My colleagues working in biochemistry work on that. So the part of my job is to understand how that organic chemistry occurred. Well, let me say that there are also new achievements. So these milestones are changing a little bit, especially as far as the timeline is concerned. In fact, there is now evidence from a little zircons found in Australia that maybe the oceans were already present 4.4 billion years ago, so a little bit earlier. And then there is, I loved very much this, this work. It's very intriguing because inside one of these little zircon, they found a small dot of graphite. Also, we say, who cares? No, we do care. We do care because this small dot of graphite has a peculiar property. There is the same ratio of carbon 13, carbon 12, which is typical of living entities. So this is really a strong clue that this might be actually a very small living entity that gets burnt inside the zircon while there was this probably volcanic eruption or whatever. And so not everybody agrees on this, but that would be even indicating that actually we had life, not organic chemistry, life 4.1 billion years ago. So everything maybe was faster than what we thought until not so many years ago. And so there must have been a way to have this organic synthesis in a very efficient way and in a shorter time in a shorter time lapse with respect to what we thought. Okay, as a chemist, what do I see here? I see an environment dominated by water and then organic chemistry. So if you ever in your life study some organic chemistry, you probably know that water is not a good solvent for organic synthesis. So this is a paradox in a way. So how is it possible that we had such elaborated organic chemistry in an environment dominated by water that is the enemy number one of organic synthesis? So it's really a paradox. And think also how this could work. And I like very much to talk about quantities. So now it has been estimated, it's not easy to have this number, to get this number out, but it has been estimated that if you consider all the all the living entities now on Earth, the global mass is 5.5 times 10 to 14 kilograms. And you have to compare it to the amount of water. So it's really a tiny fraction. And so even now that, we had a life for all these billion years, that's the amount of carbon which enter into life. So compared to water. So how this could really happen? So it's not obvious at all. So that's why there are actually two possible explanations to explain this chemistry that should occur not on liquid water. And so one possibility that you certainly are familiar with, and I think that most of you actually work on the second possibility, the so-called exogenous delivery. Why did we think about that? Well, because all these small objects that I put in the pictures, all of them are very rich in organic compounds. Some of these organic compounds are also complex, are already complex enough. In turn, that means that these carriers and somehow they bring the heritage of the star formation, star forming regions in the interstellar medium, where we do know again that there is a lot of organic chemistry going on. Not only that, when we see that in the Orion Nebula, whatever, I see a molecule like from a mile remotely using your beautiful radio telescope and so on. So that means that to have that signal so far away, the amount of this stuff there is huge for our standard. It's huge for, okay, it's not huge relatively, but it's huge for our standard. And that's an important point. The alternative is the so-called endogenous synthesis, and of course it dates back to the experiment, the groundbreaking experiment of Stanley Miller, um, and that you have to involve in your chemistry not the water, or also the water, but a more complex system where the gas phase is also important. But let me say that the experiment by Stanley Miller in its original design is a little bit, what can I say, the mixture was not the right one. So if you repeat the experiment of Stanley Miller with the right mixture of gases, we probably were the primordial atmosphere of Earth, and then the things are not going so well. So there are some mysteries. Okay, there is one last possibility that, of course, I need to mention. It's a possibility that this chemistry occurred thanks to the hydrothermal vents in the oceans. Well, of course, the reason why we are interested in prebiotic chemistry in space, that was the title of my talk that I'm trying to explain to you. Well, exactly because of that. So we have to understand where this prebiotic chemistry occurred. The idea that it was a legacy somehow, the chemistry occurring in the stellar medium, in my opinion, is very interesting and is it has a lot of good points, I would say, because in all these different stages of the life of the star cycle, we do see organic chemistry. We do see organic compounds, and again, according to our standard, in a huge amount, actually, in a huge amount. And then, of course, the idea that somehow this chemistry was brought to our planet after the liquid, after the hydrosphere was formed, is of course sustained by many pieces of evidence. Okay, I'm not going to teach you about the birth of solar systems because, of course, you know this much better than me. But I'm representing here this simple scheme just to try to unveil some aspects, because there is a question, in my opinion, that is very important. I have a chat now with Eugenio and his collaborators about this, but it is something that I really like. So the idea is that, not the idea. So what do we see? At least in our case, in the case of our solar system, well, internal rocky planets are seriously depleted of volatile species, and there is explanation, there are explanations for it. But let me add something that maybe you don't think often of. The rocky planets are also strongly depleted of carbon, in general. Okay, there should have been another slide. Okay, doesn't matter. Okay, so when I say depleted of carbon, well, I know that it's not so easy actually to have these estimates and everything, but for sure, if you look at the estimated abundance of the chemical elements in the solar system, well, you see there, this is a logarithmic scale that is even cut, so it's not so clear, but carbon and oxygen are roughly present in a similar amount. Okay, oxygen is more abundant, but not so much, factor 2 or something like that. Well, in the case of Earth, well, here the situation is very different. So our planet, where organic chemistry, that is the chemistry of carbon, is at the base of our life, but our planet is strongly depleted of carbon. So something you really don't expect. The only planet where you see life, which is a form of organic chemistry, so chemistry of carbon, chemistry of reduced carbon, and then carbon is actually not so abundant. So maybe you expect something different, that you had this chance to have this organic chemistry and blah, 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 that brought to life in a region where you had plenty of carbon. Instead, we are deprived. And not only there is a little amount of carbon, but most of the carbon on Earth, still now, is in the wrong form. The wrong form is the fully oxidized carbon version, which is CO2 or carbonates. So actually, most of the carbon on Earth is in the form of carbonates in the lithosphere. So life instead needs reduced carbon. So how does it work now? It works with the photosynthesis. So plants using the solar radiation are converting using an enzymatic catalysis, which is a very complex process that only life can do. They are converting continuously CO2 into reduced carbon compounds. Life. So how did it occur before life? So that's a big question mark, in my opinion. Okay, so there are possible explanation that explain this the missing, let's say, carbon. So carbon, I'm not an expert of this, so I feel embarrassed to speak in front of you about that. But the idea is that most of the volatiles are probably gone if you are within the frost line. So when rocky planets accrete, and of course our is rocky planetesimal, sorry, we are the rocky planet, and we start with rocky planetesimal. And so maybe there is no obvious explanation why we still have a lot of oxygen, because of course oxygen is in the silicates that form this planetesimal. Not only silicates, but also water embedded in these silicates. So that's probably carrier of oxygen. And so you say, okay, the problem is solved. This is the reason why we do see them. Well, yet in meteorites, but also in interstellar dust particles, we do see not only silicates, but also other refractory compounds, and these are compounds of carbon. So there are a lot of refractory forms of carbon. So why this refractory carbon is not conserved during the planetesimal of rocky planets? It's not a volatile. Okay, so where are the refractory forms of carbon? I don't have answers for this. I'm asking you. I'm asking you. So something happened, not only having in mind the origin of life, actually, the importance of refractory carbons is extremely relevant because it is in the reduced form. So the form which is right for life, not in the oxidized form. Okay, so there is something to think here. I don't have any answer. Let's think about quantities. Okay, so you probably have seen already this image. This is an image by NASA. It's a very beautiful image because we are used to see our planet covered by water, and so we might think, oh, our planet is a planet of water. But instead, in the image on the right, you see that that large drop is actually containing all the water of the superficial water, because we don't know how much water is inside actually. And so the diameter, as you can see, compared to the other part of the planet, and the smaller dot, that's fresh water. It's only 2% of the global water of the planet. Okay, so when I saw this image, I think, okay, I want to draw here a small sphere containing all the mass of living entities. Everything, every planets, microbes. All the living entities on the planet. I couldn't because it's much smaller even than the fresh water. So these are just, to play a little bit with this idea, comparing the total mass of the biota with water and earth. So why am I saying this? Because really we are, can I say this word, we are a speed on the planet, really a small quantity. If you think, of course, of the entire mass, life is really maybe a marginal phenomenon in a way, if you consider the entire planet. Okay, so I'm trying to make my point in some way, but everything occurred, and so we are so happy about this because we are commenting about that exactly because because finally life originated. So when I say prebiotic chemistry in space, what do I mean? What are we searching? Well, in a sense, everything is prebiotic. Even a proton is prebiotic in the sense that preceded life, and it was probably important. It was there at the right moment, and so on. But in my opinion, the molecules that I'm more interested in are this kind of molecules. So these are unsaturated species containing carbons, the gray the gray dots there, and nitrogen, for instance. Why is specifically this one? Because the presence of multiple bonds that you might recognize in those structure makes this molecule very reactive. And this molecule, when they are in contact with the liquid water was there on Earth, primordial Earth, well, they undergo some processes called hydrolysis, and they form actually, oxygen is part of life, and so they have nitrogen, they have carbon, they have hydrogen, and then you make oxygen entering. So these are, in my opinion, some of the most interesting species that we might search around in the universe. And so have they been observed? Well, of course they were. All the molecules that I've drawn there have been observed in the interstellar medium, and especially in star-forming region, not only there. And so this is just a list of the molecules. Probably it's not updated now. There are almost 300 molecules, and a large fraction of these molecules actually contain carbon. It's not a surprise for me. It's not a surprise for a chemist, because carbon can form a lot of molecules. And if you look at the list of the elements, the most abundant is hydrogen, then helium does nothing, oxygen. So how many molecules can you form with oxygen and hydrogen? Two, water and hydrogen peroxide, that's it. How many molecules can you form with only hydrogen and carbon? Millions. So the organic chemistry. And then if you add oxygen and nitrogen, then really it has been estimated that all the possible organic molecules that can be synthesized, I don't remember the number exactly, but it's something 10 to the 22. That's all the possible combination of carbon with oxygen, hydrogen, nitrogen, and few other elements like sulfur. So it's not a surprise in a way that we do see these molecules up there. It's not a surprise at all, not only in the interstellar medium, but of course also in the small bodies that are formed in the periphery of that were formed in the periphery of our solar system. And so their amount of organic molecule could be preserved far away from the central star. So prebiotic chemistry only in the interstellar medium? No, not really. So there are other possibilities. And in fact, I'm also interested in this other part, because there is a special body in our solar system. It's not a planet, it's a moon. It's a moon of Saturn, but it's larger than Mercury, so it's a kind of it's a massive moon. And so I hope I will have time to speak a little bit about this, but there are alternatives. So there are alternatives. Prebiotic chemistry can also be done locally, as it is in the case of Titan. This is really a bizarre moon, because it has a very thick atmosphere. Not only it's thick, but it resembles very much our atmosphere, in the sense that molecular nitrogen is the dominant species, as it is in our case. But in this case, there is no oxygen around. There is a lot of water on Titan, but the temperature is so small, it's 92 Kelvin, that it is actually as tough as rock, and it is on the surface. Oxygen is not around. And the second most abundant component of Titan is methane. And then there is this incredible complex chemistry. And what is really interesting, in my opinion, and that came after we know about that after the Cassini-Huygens mission, the complex chemistry which is occurring on Titan, and that brings to the formation of very complex organic species with a mass of up to 8,000 Dalton, actually also 10,000, 11,000 Dalton. This chemistry is occurring in the thermosphere, in the most rarefied part of of the atmosphere of this moon, not as it was believed before in the stratosphere. So that means that there is a way to synthesize very complex organic molecules. I repeat, these are organic molecules containing nitrogen. So unsaturated nitriles, the molecules I like, because they can really be precursors of biochemical molecules with biochemical relevance, for sure. This chemistry is occurring in a very different way with respect to what Stanley Miller thought. In the upper part of the atmosphere, the liquid water is not involved at all, and we do have this incredible chemistry occurring. And as I said, this happens in the upper part of the atmosphere. Not only Titan. A very similar situation has been found also on Pluto. which is much far away, so it's much colder and everything. So the atmosphere of Pluto is not even stable for its entire orbit. So there are episodes where there is an atmosphere and episodes where most of the gases are actually frozen on the surface. But it has been seen that there is a similar chemistry going on up there. So either in the planetary atmospheres, there is this chemistry. Most of the chemistry is occurring in the gas phase. For instance, in the case of Titan, simple prebiotic molecules, but even not so simple in the case of Titan, for instance, can be formed totally abiotically, so there is no life there. And so these molecules could have accumulated and formed this huge amount of, huge amounts, a large amount of organic compounds from which somehow life arose. Okay, I have a little list here. These are molecules that we do find commonly in space. These are on the left column, and they are potential precursors of the other molecules on the right column, and these are the molecules of life. So there is a clear link among these two families of molecules. Okay, so let's say that somehow these molecules formed abiotically was brought to Earth, but we have to ask ourselves some other things. Is it easy to do? Well, not really, not really, but they are there. So part of my work has been to understand how they are formed in these very harsh environments. For instance, like interstellar space, so that's really not a situation where you expect a lot of organic synthesis. And so we ask ourselves how it is possible these molecules are formed up there. So what is wrong with the interstellar medium? Well, first of all, the low number density, which can be as low as 10 to 4 particles per cubic centimeter. So that means actually that you don't have species meeting each other. And to have chemistry, of course, you have to have a molecular encounter. So that's the first problem. The other problem is the very low temperature. Some of these regions have a temperature which is as low as 10 Kelvin. So you might think that nothing happens there. Instead, these are the regions where we have seen the most complex molecules at the moment, like naphthalene, also cyanonaphthalene, say. Why it is a problem to have low temperature? Well, because most of the chemical reaction need to overcome a little energy barrier. Also in the cases where actually the reactions are exothermic, so they actually liberate energy. Even in these cases, you must spend some energy to promote them. So that's another problem for this. And so how were they formed? Well, if looking at the interstellar medium, we know that by mass, 99% of it is in the gaseous phase, but then there is 1% which is in the form of dust. Dust particles are covered by icy mantles in the region where the temperature is very low, so they could give a contribution. So that's roughly the status of our understanding of what's going on. So we know that in dense cloud, where the temperature is very small, there is some chemistry occurring on the surface of the dust particles that then becomes covered with ice. It's a kind of simple chemistry for sure. So in particular, you have the hydrogenation of several species. This is a very relevant point. It's a very relevant point because, for instance, CO is converted into methanol, and methanol now can be converted into organic species. So that's really an important part because, as I said, it's not so easy to convert oxidized carbon into reduced carbon. And so there is a consensus on this. And then there is no consensus, but there are actually two paradigms. What happens after this first step? So either you have the release in the gas phase of these simple hydrides, molecules formed by hydrogen addition on the dust grains, or you keep on having all the chemistry occurring in the ice. And as in this case, there is no consensus. Actually, the two scenarios, I mean, there are very hot debates about this. But anyhow, we do have some chemistry occurring there. So either promoted by dust particles or totally in the gas phase, definitely we have plenty of chemistry occurring there, even though the conditions are so extreme. And to understand this chemistry, we must rely on this multidisciplinary approach. That's why I'm in this business, because of course you have astronomical detection that are going to tell you which molecules are there and also their relative abundance, another piece of information which is very important. Then it is important to run astrochemical models. Astrochemical models should be able to reproduce the observed abundance and of course also the detection. And to have accurate astrochemical models, there is the need to have information from lab experiments or also theoretical simulation. Of course, in the astrochemical models, there is a physical part, but there is also, in many cases, an important chemical network of reactions. And it is very important to have accurate models that the chemical reaction are correct. It's not always the case in the interstellar medium. Astrochemical models, normally there are included roughly 8,000, but even more, even 11,000 in some cases, reactions that include all these families of processes, including the heterogeneous processes occurring on dust or the icy mantle of dust particles. And what's our knowledge of these processes? Well, most of these reactions have never been investigated actually. So they've been included in the model with guessed parameters. Only a small percentage has been characterized in lab experiments yet. And so I work with neutral-neutral reaction, one of these families of processes. And I can tell you that for neutral-neutral reaction, there is a concerted effort that really help us to understand what's going on. So the approach is based on 3 pillars. So essentially, we have a technique, a very powerful technique that is able to reproduce the low temperature of interest in the interstellar medium. It's a fantastic technique that it has revolutionized twice, actually, our knowledge of chemistry, because there were, some some ideas that then were proved wrong exactly by this kind of experiments. But it is able to reproduce the low temperature environment, but not the low pressure environment. And then there is the other technique that I'm using in my lab, and it's not only me, there are also other labs around the world. And in this case, we are able to reproduce the very low pressure. Okay, not exactly the same pressure, but it doesn't matter because it's enough to reproduce the so-called single collision conditions. And so that means that we can really investigate what happens when one atomic species, for instance, like in the animation, is meeting a molecule, and then the products reach the detector in our conditions before undergoing any other collisions. And so in this way, we are able to simulate the very rarefied conditions of the interstellar medium. That's just a real picture of my machine. I don't want to give you details and everything, but let me just say that with my technique, we are able to tell you which are the products of each reaction. And this is an important piece of information because in the models, the reaction of one process, of the products of one reaction will become the reactant of a subsequent one. So if there are mistakes there, the entire network is wrong. Just a list of systems that we have investigated in my lab. Some of these reactions are of relevance in the chemistry of the interstellar medium, some other in the chemistry of Titan. That's why I know that case very well, but also in the chemistry of comets. It's not only me, as I said, there are many other labs working on that. In particular, there are the lab by Ralph Kaiser in Hawaii that are producing a lot of data that are relevant for this for the chemistry that we are dealing with. My technique is also very good, but it's able to reproduce the low number density condition of interstellar medium, not the temperature. And so you cannot have everything. Okay, so we need a third pillar, which is the theoretical treatment of chemical reactions, because in this way, by joining the information that you get from the first, from the Kresu technique and from my technique, we know everything. And so we are finally able to have the right description. So that's our combined approach: 2 experimental techniques, a theoretical approach, and we know everything. So once we derive this quantity, which comes from the theoretical work, well, then we can predict everything. So in my opinion, we are very good with gas phase reactions. And thanks to the theoretical treatment, not only we are able to put together all the information that you got from the experimental techniques, but in some cases, in some cases, clearly, there will never be experimental data because this chemistry is very difficult to reproduce in lab experiments, especially when the chemistry involve strange radicals. Also, Jen, you were showing me now these reactions which are almost impossible to study in experiments because they involve two transient species, and already to produce one is a nightmare. To produce them is a nightmare to the square. And so a theoretical approach can really help us to understand what's going on. At least and it can give us an educated guess and not just a guess, as it has been done for years. Okay, so I don't know if I have a lot of time, especially because we had all these problems. So there are some cases here that I will skip. I'm sorry because they were very successful examples, but let me just say that, okay, let me say success in the sense that we were able to derive, not only to derive, but also, for instance, to explain the isotopic enrichment of a glycolaldehyde, for instance, or also acetaldehyde and also acetic acid, starting from a series of reactions that we thought of. Everything started with ethanol. Everything started with ethanol, so we can reconstruct this parenthood relation, parenthood or sisterhood, in some cases relation, among molecules. Not only we are able to explain their abundance, but also some more detailed aspects, like, for instance, the iteration degree, what we call second generation organic molecules. Another molecule that we succeeded to also to give all these details is formamide. We proposed a formation mechanism of formamide, and not only this approach is able to reproduce some detection that have been done in a very well constrained situation, but also we have been able to actually to reproduce, actually to anticipate the deterioration degree of formaldehyde, to explain the amount of deteriorated formamide. So forgive me if I'm not giving detail, just believe me, but I can explain more later. And so another case of success, because we were dealing with the so-called kinetic isotope effect, something that has been totally overlooked until recently. Because I've heard many talks in the past saying that the deterioration of molecules of reactants in the gas phase is transmitted to the products as such. This is not true. This is very well known, actually, in chemistry, that is not true. And thanks to this trick, maybe we are able to really pinpoint the origin of some prebiotic molecules, because both glycolaldehyde, the simplest sugar has been defined, and formamide have a strong prebiotic potential. Okay, so here as well, I'm jumping a little bit. Okay, so if I have at least a few minutes more, I will take my shuttle, my Enterprise, and going from the interstellar medium to Titan, because Titan is really an amazing case to study prebiotic chemistry. So really amazing. So there has been a tentative detection of pyridine, which has not been confirmed at the moment, actually. And the pyridine is this molecules that you see here. So what is so special about this molecule? Well, actually, this is the special molecule, which is pyrimidine, and which is related to the other one. And so there are three nucleobases, essential components of DNA, that have a pyrimidine, so this guy here, skeleton. So it was really cool. It was really intriguing to see if the chemistry in Titan is so complex that it can form the precursors of nucleobases, and then possibly DNA. The reason for that, the reason why it is possible is because this rich chemistry occurring in the upper atmosphere, that's a very strategic point, the very strategic aspect. We know that brings to the formation of these very complex species, and there are clues that there are aromatic species, these special molecules with aromatic rings, very resistant actually to the chemical attack. And so there is plenty of evidence that there are these compounds up there. And so we wanted to understand if this chemistry can start from simple bricks and then leading to those species. And so of particular importance is the activation of nitrogen. Molecular nitrogen, maybe you remember from your chemistry studies, the molecule of nitrogen has a very strong bond. It's very difficult to activate it. So practically, you can break a molecule of nitrogen only in the extreme ultraviolet. You need photons below 100 nanometers. And in this condition, nobody really expected that there was this chemistry occurring on Titan because it's so far away from the sun. Yet the flux of photons is enough to produce a significant amount of these species by breaking up the molecule of nitrogen, and this is occurring at 1,000 kilometers on the sea level, no, because you not see no sea there, but of altitude. And these species can react with all these suites of organic molecules that are formed there for a series of reasons, and in particular benzene. There is a huge amount of benzene on Titan. Benzene is the simplest aromatic compound. And actually, not only it has been detected, but it has been detected at various altitudes. And the largest molar fraction for benzene is around 1,000 kilometers of altitude. I cannot see on the sea level because there is no sea on Titan. And as you see exactly where there is plenty of these very reactive species of nitrogen. And so we investigated the possibility that you had this sequencer, okay? So forming from benzene directly pyrimidine, the skeleton of nucleobases. According to theory, that was possible, but I have to say that during the experiments, unfortunately, they find out that no, it's not possible. So I mean, it's important to make this effort to pinpoint the processes that they can really occur there or elsewhere. And even though sometimes chemistry or chemical intuition can suggest that these processes do occur, for instance, when then you go study them in the lab, unfortunately, you see that they cannot be formed. Well, there is plenty of gas phase chemistry occurring either in the atmosphere of planets or exoplanets also, or in the interstellar medium. This can lead to a lot of complex chemistry, and that's important. So there are, especially when you have the presence of hydrocarbons, that really gas phase chemistry can lead to the formation of also macromolecules. So the answer to the question is easy or not easy? It's not easy. It's not easy, but possible. Not easy, but possible. And not only in the environments that I mentioned, uh, space mission actually are helping a lot to understand what's going on. I'm reporting here 3 specific missions, Cassini-Huygens, Rosetta, and New Horizon, because in all these 3 cases, the organic chemistry, the chemistry and the organic chemistry that was found in those objects is much more complex than what is believed before the missions. So there is still a lot, really a lot to understand. And small bodies, that's another frontier. I love this subject because really in small bodies of our solar system, there is plenty of organic chemistry going on. We do see them. And what about exoplanets? Well, exoplanets they are totally to be explored. And of course, you might be aware about the biosignature problem. So by observing an object with what we can do, for instance, in the infrared, is it possible to understand if there is life or not? And this is a nice spectrum, actually, the emission spectrum of our planets in the thermal infrared. And as you can see, there are these typical bands in the case of Earth that are associated to life, but which of them is really associated to life? So ozone is a possibility. This is water vapor can be present in many cases without any life. Ozone can be a good candidate, but there could be also false positive. This is a recent spectrum taken by James Webb, and I see a molecule really intriguing there, dimethyl sulfide. Dimethyl sulfide is very interesting because there is reduced carbon and reduced sulfur. So there is really a lot of this chemistry occurring. And so we know it happened once at home. So our idea is that we go, I mean, this is the way that we like thinking, that we go from very simple species, join them and make them a little bit more complex, and then this increase of complexity. We saw them in a continuous way, but was really that way? We don't know. So we know that we started with physics.
Can I ask you to wrap up?
Yes, that's the last slide. So we started with physics. We end up with the biology. In between, we think we have chemistry of increasing complexity, but maybe it's not so. Maybe we go to more complex chemistry and then go back, like in the case of Titan. And we know it happened on Earth. And so, of course, the big question is, did it happen elsewhere or can it happen elsewhere? Well, we don't know, but I'm sure that by studying the organic chemistry that we see in space, at least we can set the stage for that to occur. And that was really my last, sorry for all the inconvenience. Thank you for that.
Sorry for the inconvenience that we had initially with the audio system. So, time for question. So, if anyone has a question, I see a question in the audience.
Yeah, I have a technical question, so sorry about that. When you deal in your lab with molecules and reactions, especially the single molecule phase, and you said that at low temperature, a lot of reaction are possible. So it's to me, it's really mysterious the concept of temperature. So how you, handle the temperature with such a case? I mean, temperature is a concept which is a statistical
Well,
concept.
Don't tell me because I've insisted a lot with my colleagues during the modeling that actually they should consider cross-section as a function of the energy and not rate coefficient as a function of the temperature. But so at the moment I will see go more. Yes, I totally agree. When the medium is very rarefied, you don't have this thermal equilibrium. Or you might have it, but in a very long time scale. So that's actually the answer. Since we are considering an evolutionary time of million years, so you can consider that on average is the same. I'm not sure. I'm not so convinced because in many cases my feeling about this is exactly that you might have multiple processes in when you have a very dense gas. That will never happen when it's so rarefied. It's not just a matter of time scale, in my opinion. I totally agree with you. Totally agree with you. Maybe for in the case of gas grains, the concept of temperature is better defined because, of course, they consider the black body emission, so that should be a little bit safer, I think. But when you go to gas phase so rarefied, in my opinion, temperature is ill-defined. I totally agree.
So, another question, I see Sergio here.
Yeah, so why only Titan?
No, not only Titan, but Titan is the most interesting case in our solar system, no doubt. So that's the body in the solar system with the richest atmospheric chemistry, much richer than ours. And the reason is exactly that. Since there is no oxygen around, oxygen is a killer of organic chemistry. Never forget it. Since there is no oxygen around, because oxygen is kept as ice on the surface, 94 Kelvin, so really no sublimation, almost no sublimation. And so there is this 4% of methane instead. And so organic chemistry starts, there is nothing there that breaks it apart. That's the question. Of course, ultraviolet photons, but that's an interesting thing. So when you have an organic, a bulk of organic compounds, and you have UV photons, so we are used to think that UV photons destroy organic compounds. That's true. That's true, but they transform them in other organic compounds. You don't lose carbon in that case. To lose carbon, you need oxygen because then you form CO and CO2, and that goes to the gas phase, and then you lose it. I've seen that there are actually many small objects, like for instance Ceres, where there is this kerogen-like stuff. So many of the small bodies in the solar system are covered by this kerogen-like stuff, which is probably what is remaining of carbon or organic compounds once UV photons hit them. But carbons remain there if you don't bring it to the gas phase. So oxygen is the killer of organic compounds, not UV photons.
There was no oxygen in the very early stages of Earth.
Yeah. No free oxygen, but water, UV photons, and then you have oxygen again, or oxygenated radicals. Like these are the real, for instance, OH radicals. OH radicals are able to degrade organic compounds.
Any other question? Let's see.
Yeah, out of curiosity, actually. So typically, is the habitable zone considered to be the distance in which it could be liquid water at a certain distance from a star? But you were saying that probably water is not actually helping a lot for complex chemicals. But
Okay, that's a kind of paradox because life needs water. In a cell, 75% of cells is water. So life needs water. The water is an enemy of organic synthesis, and it's also an enemy of, it's a possible generator of oxidizing radicals. So that is really a paradox there. So you must have had somehow a bunch of reduced carbon compounds brought, I don't know, or formed like on Titan. So there are suggestions, if anything similar to the case of Titan ever happened on Earth. So now, on Titan, nothing else happened in the sense these molecules formed, they are very large macromolecules, so at the end, they will be deposited on the surface of Titan. In fact, the surface of Titan is full of this strange thing called like sand, let's say, but it is done by, the components are actually these macromolecules containing carbon, hydrogen, and nitrogen. So these molecules when they precipitate on Titan, they found a frozen world and they don't the world further. But you imagine the same molecules on Earth, big if, the same molecules on Earth, if they were falling down, they would meet ocean. Then they hydrolyze these reactions with water. And then you will have immediately compounds with carbon, nitrogen, and oxygen, which is also important for life, sugars and everything. So oxygen is important for life. So if anything really similar to what happened on Titan happened on primordial Earth, the same molecules falling down formed in the thermosphere, big if, but if these molecules then falling down, they touched, in this case, liquid water, poof, life, or precursors of life. We know that because these molecules on Titan are reproduced in lab experiments. These are called tollings. Maybe you heard about this term. And tollings are compounds with a lot of hydrogen, nitrogen, and carbon, same ratio as those found on Titan. And in the contact with water, they hydrolyze and form both amino acids and nucleobases, really biochemical molecules.
Go, Alessio, and then.
Just a very simple, naive question, but it came up again in my mind now that you said the life or precursors of life. Now, part of the discussion was from prebiotic molecules to more complex amino acids like life kind of molecules. So, from a chemistry point of view, what exactly is the difference from a prebiotic molecules and a life? What do we call life molecules with respect to a prebiotic molecule?
Okay, you can have biochemical molecules, that is, molecules that are used by biochemistry that are not life, of course. So if I take a molecule of glycine, we cannot say that's life, even though glycine is an amino acid. So these are the molecules that life uses. Okay? Of course, they are not life. But the biomolecule is a molecule that life uses. Prebiotic chemistry is everything that leads to these biomolecules in an abiotic way. That's the point. We think, we don't know if it was the way it went. So it's just our logical way of thinking that suggests us, okay, first you must have had some mechanism bringing to the formation of these molecules, and then these molecules, with a mysterious mechanism because we don't know it, they started to organize themselves, leading to the first form. The first form, it is not necessarily what we see now, so that maybe that came later, but since they were more efficient, then they took all the resources. So we don't know which was the first replicating molecule, let's say, from which everything started. We don't know. Simply don't know.
I think there was another question.
Yeah, it's actually one curiosity. I was wondering, many of the organic reaction should happen with some energy, output of energy, like UV or So I wonder if this might be actually the right situation on the Earth being so close to the sun.
Okay, so here as well there is a kind of a Goldilocks situation. So you need energy to
Yeah.
promote chemistry, but not too much energy because then you destroy them. It's a kind of a delicate balance.
Or maybe the temperature was there.
The temperature, okay, normally if you increase a little bit the temperature with respect
You
to the
destroy
room
it.
temperature, no, well, actually you
Yeah,
facilitate
because
the chemistry.
there are some of these aldehyde things that
Probably if really, life, I mean, originated in that, I mean, before actually, I mean, there was a total cool down of the surface, that's another possibility which is considered. So maybe a temperature of 50 degrees was good enough to promote chemistry without destroying the organic molecules. Also because we were supposedly in the absence of oxygen, because then if you warm too much organic compounds in the presence of oxygen, then you have again oxidation.
Yeah, without oxygen,
Without oxygen, a
enough
little
energy,
bit,
a little bit of energy.
that helps, and it is not necessarily destroy them. So also UV photons actually, because
Yeah.
organic compounds are sensitive to photooxidation rather than simply photodissociation. Okay, there is also photodissociation, but as I said, once you photodissociate an organic molecule, you form organic radicals. These organic radicals then react by themselves, and maybe they form even more complex species. So if there is no oxygen around, that's good. Oxygen around is a problem because then they are converted into CO, CO2.
Certain Titan is not the Earth.
Titan is fantastic because there's no oxygen around. Just a very tiny amount of CO in the upper part, but really a tiny amount. In this respect, yes. That's why I said a big if in the case of Earth, because I don't think, certainly there was not that kind.
No.
I don't know. Probably it was more similar to what we see in Venus or Mars.
Yeah.
But I've seen some simulation that with a little amount of, not the main component, but for instance, if you start from CO rather than CO2, it's already working a little, not as good as in this case, but CO is still spendable. When you go to CO2, then you really, here, you know that, we have also this climate problem because of the accumulation of CO2 in air. So only plants, only the photosynthesis is able to get rid of CO2. Otherwise, the lifetime of a molecule of CO2 in atmospheric air now, in our atmosphere, is very long. It's more, it has been
Probably
more than 200 years.
became in another state with the oxygen too.
I think that most of, I mean, the secrets of our study, I mean, the trick was the relative ratio between carbon and oxygen. And also in a region so depleted. I mean, what really hits me in a way is that we have a life in a planet depleted of carbon. that's a or maybe if it's not so, maybe this refractory carbon that is missing to our inventory, maybe it was the player. Where is this refractory carbon?
So I don't know if there are any more questions. I think the discussion is extremely interesting. Just want to conclude with a comment from my side. It seems to me that there are some basic ingredients to go from molecules to the prebiotic molecules, but there are also some very fine tuning in some cases, because you need you need water, but you don't need an environment to reach on water. You need energy, but you don't need. So how much tuned should be this range of external condition to really proceed with life? We know that it worked in our solar system.
We need another example.
Yeah.
We cannot do a statistic with one case.
Yeah.
So we would need another case at least, but who knows? Who knows?
Anyway, thank you, everybody. Thanks to people at home and for their questions. Especially, sorry for the inconvenience. I hope that you enjoyed the seminar anyway.